Today we also discuss non-linear space. Some example we also check here. This one is vector space or not. Okay. We also check this example now. L infinity k. Okay. L infinity k, the set of all bounded sequence in k. Okay. We also write here x such that those sequence xn in k such that xn be bounded. Okay, now we also check this one is vector space or not. That means for x equal to xn and y equal to yn. Okay, in L infinity k. Okay, now x plus y equal to what? X plus y equal to simply x1 y1 x2 y2 dot x k k. Okay, dot x and y n. Now this one is, that means bounded, since x equal to xn and y equal to yn belongs to L infinity k, then there exists m1 m2 greater than equal to 0 such that norm of xn less than equal to m1 and norm of yn less than equal to m2. Okay, for all n belongs to n. Okay, then this gives norm of xn plus yn less than equal to norm of xn plus norm of yn less than equal to m1 plus m2. Okay, for all n belongs to n. So this one is x plus y belongs to L infinity k. Okay, then addition be closed on L infinity k. Then this be closed in L infinity k. Okay, this operation be closed in L infinity k. So L infinity k plus L infinity k plus be an abelian group. We erase that portion and going to further discussion of that. Okay, now for lambda belongs to k, x equal to xn belongs to L infinity k. Okay, then lambda x equal to lambda x1 lambda x2 dot lambda xn dot. Okay, equal to lambda xn. Okay, n equal to 1 to infinity. Then what happened? Then we also check lambda x, okay, is bounded or not. That means lambda x n. Okay, this one less than equal to norm lambda norm xn less than equal to norm lambda m. Okay, if norm of xn less than m for all n belongs to n, then lambda x is in L infinity k. Okay, so all the assumption of linear space hold, then L infinity k be a linear space or vector space. Okay, over k. Obviously we write here over the field k. Okay, next we erase that portion and going to discussion about that portion. Okay, xn is bounded, then this one is, that means done. Now we're also going to L1 space. Okay, we erase that portion and going to discussion about that. Yeah, L1 space. Okay, L1 space, that means let xn be a sequence in k. Let xn be a sequence in k. Okay, then summation n equal to 1 to infinity xn be absolutely convergent, be absolutely convergent if summation n equal to 1 to infinity mod of xn less than plus infinity. Okay, then this one summation n equal to 1 to infinity mod of xn less than plus infinity implies that summation xn n equal to 1 to infinity be convergent. Okay, be convergent. This implies that xn tending to 0 has n tending to infinity. This implies that xn is convergent and converges to 0 and converges to 0. Okay, this implies that xn be bounded. Okay, then here n be a field and a countable set Ln can also be written as L this index set delta. Now also show about that. That means L1 the set of all sequences in K summation of xn less than plus infinity. Okay, then L1 K equal to those x equal to xn such that, okay, xn in K such that summation n equal to 1 to infinity mod of xn less than plus infinity. Okay, now we're also going to discussion about that L1 key be a vector space. We have to show that. We erase that portion and going to further discussion of that. Okay, we need to show that L1k be a vector space. Be a vector space. Okay. For x equal to xn and y equal to yn. For x equal to xn and y equal to yn. Oh, this is visible? Not. Why this is not visible, I don't know. Oh, something is problem here. Who created those problems? I don't know. Some obviously some bastard are create this problem. Oh, why this they are created some problem? I don't know. Now I think this one is visible. We also start now. Okay. So what happened here? Okay, L1k be a vector space. X and y belongs to L1k, and then x plus y equal to x1. Here we write in this way: x1 plus y1, x2 plus y2, dot 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 xk plus yk. Okay, then note that summation n equal to 1 to infinity mod of xn less than plus infinity. Okay, and summation n equal to 1 to infinity mod of yn less than plus infinity. So summation n equal to 1 to infinity mod of xn plus yn less than equal to summation n equal to 1 to infinity mod of xn summation n equal to 1 to infinity mod of yn less than obviously plus infinity. Okay, so xn plus yn belongs to L1k. Again, we also so simple that here alpha belongs to k. Summation n equal to 1 to infinity alpha xn less than equal to alpha mod alpha summation n equal to 1 to infinity mod of xn. Okay, less than plus infinity. Then what happened? Then here alpha xn belongs to L1k. Okay, then what we get from that L1k be a linear space. Okay, also check this two now. L infinity k be linear space or not, and L1k be linear space or not. Now we're also going to one discussion about that. We'll erase that portions, and also discussion about some lemma. Okay, then we're going to discussion about LPK be norm or not. Okay, be vector space or not. We'll also write the statement of this lemma here. This one is non-lemma for all. Okay, let alpha beta belongs to k and p belongs to 1 plus infinity. Then what happened? then alpha plus beta whole to the power p less than equal to 2 to the power p norm of alpha to the power p norm of beta to the power p. Okay, now here we write, okay, norm of alpha plus beta whole to the power p equal to less than equal to norm of alpha plus norm of beta whole to the power p equal to what? Equal to 2 to the power p norm of alpha by 2 norm of beta by 2 whole to the power p less than equal to 2 to the power p maximum of norm of alpha norm of beta whole to the power p. Okay, this equal to 2 to the power p maximum of norm of alpha to the power p norm of beta to the power p. Okay, so here alpha plus beta whole to the power p less than equal to 2 to the power p, there alpha to the power p plus beta to the power p. Okay, this one is an important lemma. Okay, we also prove this lemma now. It's too easy to handle this lemma. Now we're also going to prove that L2 be linear space or not, okay, or vector space or not. We erase that portion and going to further discussion of that. Okay, here we write L2 equal to those x n belongs to K such that summation n equal to 1 to infinity norm of x n square less than plus infinity. Okay, then what happened? We also check L2 be linear space or not. Okay, now we also defined in this way, let x equal to xn and y equal to yn, okay, belongs to L2. Then summation norm of xn square n equal to 1 to infinity less than plus infinity and norm of n equal to 1 to infinity yn square less than plus infinity. Okay, now summation n equal to 1 to infinity norm of xn plus yn square less than equal to 2 square summation n equal to 1 to infinity norm of xn square plus summation n equal to 1 to infinity norm of yn square. Then x plus y belongs to L2. Okay, now we're also going to think about that. Here that means alpha x. Okay, here alpha x we also write in this way, summation n equal to 1 to infinity alpha xn square less than equal to summation n equal to 1 to infinity, or equal to, if we write then this one is better, norm of alpha square norm of xn square less than plus infinity. Okay, then here we write alpha x belongs to L2. Okay, then L2 be a linear space. Then what happened? Then L2 be a linear space over K. Okay. Now we also discuss same portion. Obviously, if we write here LP, if we write P and here P and here P, here P, here P, okay, here P, by this lemma here P, here P, here P, okay, we're doing this one, there, here P, here P, here P, here P, here P, and here P. Then what happened? Then LP be a linear space over the field K. We also do this one. Okay. So 1 less than equal to P less than infinity be a linear space. In this way, we also discuss 1 less than equal to P less than plus infinity, and infinity also we discuss. So we also discuss that LP be a linear space or vector space. Okay. Now also known about some space, that means C0, C00, C. This one is convergent sequences. This one obviously linear space. We also just discuss this one now. Okay. So we erase that portion and going to further discussion of that. We write here C equal to those x equal to xn, okay, in K, such that xn be convergent, xn be convergent in K, okay, and this C0 equal to x equal to xn in K, such that xn converges to 0, xn converges to 0 in K, okay, C00 x equal to xn in K, such that x equal to x1 x2 dot 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 xk 0 0 dot dot dot, okay. Then what happened? Then simply we get this C0 C00, okay, are linear spaces over the field K, are linear spaces over the field K, okay. So C00 subset of C0 subset of C, okay. Now we also discuss one important topics here. This one is related here, this topics, that means x belongs to L1 implies that what? Implies that summation n equal to 1 to infinity mod of xn less than plus infinity. This implies what? This implies this series is convergent, that means limit n tending to infinity xn equal to 0. This implies what? This implies x belongs to this C, okay, or C0. This one is better because this converts to 0. Then this one implies what? L1 subset of C0, okay. We're getting this point. L1 space is subset of C0 space, okay. So we get this one. We will not check now, but this one is happened. This one are all linear spaces over the field K, okay. so easily we also write here. Now we erase that portion and going to further discussion of some function spaces. Okay, that means space of continuous functions, space of bounded functions, and the collection of k-valued functions also discussed today. Just these portions. Okay, just these examples. This one from a vector space or linear space over some field. We just write this one. Okay, we also discuss sequence space. Now we also discuss function spaces. Okay, let xy be two set, let xy be two sets. Okay, then let fx2y denote the set of all functions. Let fxy be the set of all functions from x to y. Okay, then fxk equal to what? The collection of all k valued, the collection of all k valued functions defined on k-valued functions defined on x. Okay, now what happened here? Here happened in this way. We write this one simply for if g belongs to fxk and alpha belongs to k. Then what happened? Then f plus g x equal to fx plus gx. Okay, for all x belongs to x, and alpha fx equal to here alpha f of x for all x belongs to x. Okay, then this one from a linear space. Okay, then fxk obviously from a linear space is over field k. Okay, alpha belongs to k is here. Then fxk be a linear space over k. Okay, now we also discuss the space of bounded functions. We erase that portions and going to further discussion of that. Okay, we write space of bounded functions. Space of bounded function. Okay, the function fx, the function f belongs to this fxk is said to be bounded, if there exists a constant m greater than 0, a constant m greater than 0 such that mod of fx less than equal to m for all x belongs to x. Okay, and that is supremum of x belongs to x mod of fx less than equal to m. Okay, or less than plus infinity. This one is better. Okay, then we denote this one. What? We denote f of pxk. Okay, that means the collection of k-valued bounded functions on x. The collection of all k-valued bounded functions on k, on x, okay, on x, that means from x to k, okay. Then obviously then abxk be a linear function, linear space over k, okay. Now obviously we know about one important topics. This topic is space of continuous function, space of continuous functions, okay. This one bounded function, then space of continuous function. Simply this one, let xd be matrix space, xd be a matrix space, okay. And this omega be a set in x, okay. Omega be a set in x. Then c omega k equal to what? Those f belongs to f omega k such that f be continuous, okay. Then this one c omega k, obviously we know about it, it is our portion. And so simply we also discuss this one. If fg belongs to c omega k, this implies that f plus g belongs to c omega k, okay. And alpha belongs to k and f belongs to c omega k. This implies that alpha f belongs to c omega k. Then what happened? C omega k be a vector space.